In this video, we're going to discuss rational expressions. Remember, a rational number is any number that can be written as a fraction, right? A rational number is any number that can be written as a fraction. And so now we're going to make this algebraic by looking at rational expressions. And basically, rational expressions involve the division of two polynomials such that the polynomial in the denominator is not the zero polynomial, right? And so an example of a rational expression would be something like x over x squared minus 1, right? This is an algebraic expression. It has a polynomial x in the numerator, which is linear, and a quadratic polynomial in the denominator, x squared minus 1. One thing about rational expressions is that sometimes this expression may be undefined. And so there is a restriction on the value of the variables that we can substitute into rational expressions. The reason for that is because we could potentially divide by zero. And so this statement says, since divided by zero is undefined and rational expressions involve division, there are possible values of our variable in the rational expression that cause the entire expression to be undefined. All right. And so unlike polynomial expressions, right, you can plug in any value, any real number into a polynomial function or expression and get an output of a real number. That is not the case here because we could potentially be dividing by zero. And so if I look at this example here, you could probably look at this and tell that, hey, if x equaled 1 or negative 1, then if I plug it into my denominator for x, I'll square it, I'll get 1, and 1 minus 1 is 0, right? And so this polynomial is undefined. I'm going to just write it there. So that is undefined for x equals plus or minus 1. All right. So that's something to think about when we deal with rational expressions. We're going to talk about this a lot more in detail once we get to functions and function notations and talk about what we call domains of functions. What we really want to do in this lesson here is to be able to add, subtract, multiply, divide, and simplify rational expressions. And so we're going to look at this example here, or this statement here. It says for any real number a, b, and c, where b and c do not equal 0, and the reason why we have b or c does not equal 0 is because it's in the denominator. And if we want to simplify an expression like that, all we have to do, since that's a multiplication there, that's a multiplication there, what really can happen is that we could split this into a over b times c over c, and those kind of cancel each other out because that's like multiplying by 1. And so this basically equals a over b. Now, we won't necessarily have to go through this step of separating it like this. Once I see it in factored form, notice this is a product of two things. So it's in factored form, that numerator, as well as that denominator. So once the numerator and the denominator are factored, we can cancel the terms that are common to the numerator and denominators, and then that will give us a simplified form of a rational expression. And so let's look at an example where we actually simplify the expression. Here I have negative 2x minus 4 all over x squared minus 3x minus 10. I want to simplify that expression. Notice there's a subtraction here, there's a subtraction here, and that's a subtraction there. At this point, I can't cancel anything. This x doesn't cancel with that x, or this x and that x squared doesn't cancel anything, right? Because everything is not in factored form, right? I need to see all multiplication before I start to cancel. And so let's go ahead and factor. If I factor my numerator, I can factor out a GCF, which is negative 2. And that's going to leave me with an x plus 2, right? Factor out a negative, both terms become positive. And this is a quadratic expression with the one leading coefficient of 1. So we know that factors into two binomials where x is in your first terms. And we have to find two numbers that multiply to give us negative 10, but add up to a negative 3. Well, a positive 2 and a negative 5 work for that, right? And so now that I see that in factored form, now I look across the numerator and the denominator to see if I have any common factors. And since I do, the x plus 2's are the common factors. I cancel those, and I get a negative 2 over x minus 5. This is much simpler to look at, to work with. If I wanted to graph it and all this stuff like that, or kind of make a function out of it, it's easier to work with this compared to working with this, although they're almost identically the same thing. All right. And we'll talk about what this looks like versus what this looks like later in the course. But right now, we just want to simplify an expression that looks like that. So what we're going to do is we're going to factor our numerator and the denominator, and we'll cancel any common factors that appear in both the numerator and the denominator. All right. So that's simplifying. Let's get to some other things, right? Operations. In my opinion, it's easiest to, when you're dealing with fractions, to multiply and divide compared to adding and subtracting, even though that's not normally the case. Excuse me. And so I'm going to look at multiplying fractions. I'm going to go back to numbers. Now, I'm going to do some things here that are slightly different than what you would normally do when you encounter 1/2 times 4/5. I'm going to do some things that we'll use when we actually work with fractions that are have variables in them. So what I like to do is I'm going to break this down, right? You can multiply the 1 times the 4 and get 4 on the numerator, and the 2 times 5 and get 10 in the denominator, 4/10. And then you simplify that, you're going to get 2/5. That's going to be your answer, okay? We know how to do that. But what I'm going to do is I'm going to do some extra stuff so that you can kind of see the pattern that we'll use when we actually look at rational expressions. What I'm going to do is I'm going to factor every single number that appears in a numerator or a denominator. Usually when we factor, we want to factor into prime numbers. Now, 1 is not a prime number, and it cannot be factored into prime numbers. So I'm going to keep 1 by itself as it is. 2 is a prime number, and so I'm going to leave it as 2. 4 is not a prime number. Remember, a prime number is a number that can be multiplied only by 1 in itself, or can only be divided evenly by 1 in itself, right? 4 is not prime, but the two prime factors of 4 are 2 times 2. So I know we don't normally do this, but I'm going to write 4 as 2 times 2. That's its factored form. It's prime factorization. That's the term. And 5 is a prime number, so it is already in factored form. So I went through a process and I factored all my numerators and my denominators. Once they are in factored form, now notice here, when you multiply, you can multiply all the way across the numerator and all the way across the denominator, right? But before I do that, so that I don't have to have so much multiplication, I'm going to go ahead and I'm just going to write it. Okay, I'm going to write it this way. 1 times 2 times 2 over 2 times 5, right? Because we can multiply across the top and we can multiply across the bottom, all right? Now that I have this, I can cancel my common factors, which is what we did in this example up here, right? Using this technique here. And once I have that, then I have that my final solution will be 1 times 2, which is 2 over 5. That is how you multiply rational expressions that deal with variables, right? So these are some steps here. We're going to factor all of our numerators and our denominators. I'm not going to do this step where we write them all as one single fraction, because we can tell right here and right here that those 2's are going to cancel because it occurs in a numerator here and in a denominator here. So I'm going to do it this way, and I'm going to cancel at that step. Then after I cancel, I'm going to multiply across, and then I'll simplify anything if necessary. All right. Division follows a similar process, but you got to remember that division is multiplying by the reciprocal. So what we're going to do here is we're going to take our first term, we change that division to multiplication, and we do the reciprocal of that second term. The reciprocal of 3/4 is 4/3. Now, this is basically that same type problem. Let's factor everything. We cancel our common factors and then multiply across. 1 times 2 is 2. And that's a 3 in the denominator, right? So basically with division, you have one additional step at the beginning. You rewrite division as multiplied by the reciprocal, and then you follow these same steps you followed over here for multiplication. Let's look at some example, or one example where we multiply or divide. And in this example, we actually have a division problem. What I'm going to do is once I see division, I'm going to immediately change that division to multiplication, and I'm going to multiply by the reciprocal, which means flip that second fraction. Now, we should already be experts at factoring. And so what I'm going to do here is I'm going to go ahead and factor. Now, I know, because I've done this already, that this is going to be, that's going to factor into a 3x minus 1 times a 2x plus 1. 6x squared plus 3x minus 2x, which is x, and that's a minus 1 there, all right? I factor that. Now, you may have to go through some steps to do that factoring by grouping, where you multiply the 6 times the -1, find two numbers that multiply to give you -6, and add up to a 1 and factor by grouping, right? I didn't do all of that. Just pretend that I've done it. If you need practice with that, I recommend that you go ahead and do that. In this denominator, I'm going to factor out a 3. I'll be left with a 2x plus 1. I'm going to leave my 15 here. This is a difference of squares. This is a 3x squared, and that's a 1 squared. And so by the formula of a difference of squares, I can factor that into 3x plus 1 times a 3x minus 1. Now that I have everything in factored form, I'm going to cancel everything that appears in both a numerator and a denominator. For instance, the 2x plus 1s and the 3x minus 1s, right? Also, I have a 3 here and a 15, right? 15 is the same thing as 5 times 3. And so I can cancel the 3, and I'll be left with a 5 there, okay? And so in my numerator, that canceled, and I'm left with a 5 on my numerator. And my denominator, I'm left with a 3x plus 1. And that is now in factor form and simplified completely. Now to the more difficult of the operations. Let's talk about adding and subtracting. When our denominators are the same, to add fractions, when your denominators are the same, all you have to do is go to step 3 down here. You add or subtract depending on what problem you're given your numerators. So I'll do the 1 plus 5. I'll keep my same denominator, which is 6. And then once I do that, that's 6 over 6. And then if I can cancel, which I can here, that's the same thing as 1. All right, and then I simplify. The hard part comes when we have denominators that are not the same. All right, and so when the denominators are not the same, then what we have to do is we have to factor the denominators, okay? Because we want to find the lowest common denominator. Lowest common denominator, that's LCD. All right, LCD, lowest common denominator. All right, now you can probably look at this and tell that 12 is your lowest common denominator. I'm going to go through the process of what we would do to find that, right? So I'm going to factor the 6 into its prime factorization. 6 is the same thing as 2 times 3. I'm going to factor 4 into its prime factorization, which is 2 times 2. Okay? The lowest common denominator is always going to equal the product of the factors that occur or show up in both denominators. So notice here, I have a 2 in this denominator and a 2 in that denominator, right? So that first 2 is going to be in our LCD. I have a 3 in this denominator here, right? And so a 3 is going to be in my LCD, right? I'm almost covering everything that I have in either one or both of these denominators, but I have to have this last 2 in there as well. And so this 2 here is going to be in my LCD. That means my LCD is going to be 2 times 3, which is 6 times 2, which is 12, which some of you probably were able to look at that and see that that was 12, right? And so what I want to do is I want to write these fractions with a 12 in the denominator. Well, right now they have 6 and 4. So we're going to have to multiply so that we get a equivalent fraction. Now here I have 2 2's multiplied and then a 3. This fraction starts out with a 2 times a 3 or 6. I need another 2 to get my LCD. Now I can't just multiply it in the denominator. I also have to multiply it in the numerator so that I have an equivalent fraction. And so I multiply the top and the bottom of that equation or that fraction by 2. And this one's missing a 3 to give 12. So 4 times 3 will give you 12. I have to multiply the top and the bottom by 3, the numerator and the denominator by 3. And so I'm going to get 2 over 12 plus 9 over 12. And now I'm at the point where I can just add my numerators, which will give me an 11, keep my same denominator, and if possible, I could simplify, but that's already in simplified form. All right. So let's look at some examples of when we have the same denominator and when we have a different denominator. All right, let's look at this first example here. All right, well, example 3, perform the indicated operations. In part A, we have 3 over 2a plus 3 plus 2a over 2a plus 3. Oh, this is nice. Our denominators are the same. And so if I'm going to add these rational expressions, then I just add my numerators, keep my same denominator, and then I simplify if possible. So I'm going to look at this and see if I can simplify. Now, if you notice, this is addition, so I can switch the order. Since these are the exact same term, they cancel and I'm left with 1. All right, let's go to part B. Y over y minus 1 plus 2 over 1 minus y. So these denominators look very similar. The difference here is that the order in which we subtract are different. I'm going to do a little exercise here. I'm just going to pick two numbers, 2 minus 3 versus 3 minus 2. I want to see what happens when I switch the order of subtraction. All right, 2 minus 3 is -1. 3 minus 2 is a +1. Okay, so I'm getting the opposite sign, and there's 1 there. I'm just getting the opposite sign, right? Notice that. All right, let's do another example. Let's do 8 minus 4 versus 4 minus 8. Well, 8 minus 4 is 4, and then 4 minus 8 is -4. The same magnitude, the same difference from 0, they're just on opposite sides, right? So when we have expressions that are separated by a subtraction, but we switch the actual ordering, they're just opposites of each other, all right? That's one way to think of that, okay? These two things are opposite. Those denominators are opposites of each other. And so if I want them to look the same, then I can factor out a negative. Take out a -1, all right? Then if I factor out a -1, right, that means this is going to have a negative and this negative is going to become positive, right? Factor out a -1 means you write a -1 as a multiplication on the outside and you divide each of these by -1. Well, if I divide that by -1, I'm going to get -1. And if I divide that negative y by -1, I'm going to get a positive y. Now I'm writing a little extra here so that you will see where I'm going here. So I have a negative, but since that's a plus now, I can switch the order and I can see that that's the same thing as a -y minus 1, right? So long story short, if you have a y minus 1 and you want these to be in the same order so that you can have a same denominator, factor out a -1 and you can switch the order, all right? Now, this is a positive divided by some negative value. -y minus 1. Well, when I have a positive divided by a negative, I don't have to write this negative under here. I can write this negative out front. And when you're adding a negative, that's the same thing as subtracting. So this statement is absolutely equivalent to that right there. And so now that I have the same denominator, I can subtract my numerators, keep my same denominator, and I have a simplified expression here. Remember, you can't cancel anything because they're separated by a subtraction, right? The numerator and the denominator. All right, that was an interesting example. So although it looked like we had completely different denominators, which we kind of do, we can write them as the same denominator by factoring out a negative because they are opposites of each other. All right, let's look at one more example here. I'm going to do example C, and then I'm going to want you guys to do example D in preparation for class. All right, so I have 1 over x squared minus 1 minus a 1 over x squared plus 3x plus 2. Well, we don't have the same denominator. And so when we don't have the same denominator, what we're going to have to do is we're going to have to factor our denominators and find the LCD. So I'm going to factor that first denominator. I don't care what the numerator is, even if it has some x variable expressions on the numerator. That first one factors into x plus 1 times x minus 1 because that's the difference of squares. And the second one factors into an x plus 1 times an x plus 2. There we go. And so we need to find our LCD. What I always try to figure out is what they have in common, right? They both have an x plus 1 in there. So I'm going to put the x plus 1 in my LCD. Then I throw everything else in the LCD that they don't have in common. So they don't have this x minus 1 in common, and they don't have that x plus 2 there in common. It has to be in the LCD because LCDs are multiples, and so the denominator that's common to them has to be a multiple of each denominator. So you have to have those extra pieces in there. So it's not like doing the greatest common factor, it's just putting everything in there together. And so I have this here. And so what we want to do is rewrite those as equivalent fractions. Now I'm going to do some little extra work here, right? I want my denominator to be x plus 1 times x minus 1 times the x plus 2 there, right? But both of these equations only have part of that LCD there. And so we're going to have to multiply by the one that's missing. So of the LCD, parts of the LCD that I have, I'm missing the x plus 2 here. So I'm going to have to multiply on the bottom by x plus 2 and the top by x plus 2. This one is missing an x minus 1 that's in the LCD. So I got to multiply the top and the bottom by the x minus 1. With that being said, now I have some fractions. 1 times x plus 2 is x plus 2, which is nice. And then 1 times x minus 1 is x minus 1. All right, and I just switched the order to match my denominators so that they're in the same order here. You can still write this one in that order there. Well, now that I have the same denominator, I can write this as one single fraction by subtracting my numerators and keeping my same denominator. Ooh, that's a 1. All right, let's make sure you know that that's the x minus 1 there. All right, and so notice here I put this in parentheses, and that parenthesis is needed because both of those have a negative. And so that would be an x plus 2 minus x plus 1 over that same LCD. And that equals the x's cancel, and I have 3 over my LCD, which is that right there. Notice here how I'm connecting these statements with an equal sign, equal sign, equal sign. And I'm showing you exactly what I'm doing without necessarily writing all the words down, right? So I can see step by step what I'm doing. When you're writing your math, make sure you do that because you want to be able to show me, especially when you're doing work, so that I can follow your work, what you're doing. And if you don't do that, if your stuff is all over the place, I'm not going to be able to follow you. It's almost like in English when you're writing a paper, you write your sentences sort of in order, in a flow, so that people who are reading your work is understandable. You want to get into the habit of writing math that exact same way. All right. I want you guys to do on your own. All right, and we're going to talk about it in class. And so this concludes this video. I'll see you next time.